Okay, so this lecture is going to be on the ionic basis of neural signaling, or in other words, how ions and ion channels actually create those electrical signals in neurons. Okay, so we've talked a number of times already about how neurons have membrane potentials, just like all living cells do. And what this means is that the inside of the neuronal membrane is going to be negatively charged relative to the outside. Okay, and we've already talked about how the resting membrane potential forms in neurons. Okay, so we're just going to recap that very briefly before we move on. Remember that there is a lot more potassium in the intracellular solution relative to the extracellular solution. And in addition, the neuronal membrane is permeable to potassium ions at rest because there are these potassium leak channels in the neuronal membrane. Okay, so potassium is going to move out of the cell through these open channels, down its concentration gradient. And since potassium ions are positively charged, when that potassium leaves, it's going to bring its positive charge with it. So as potassium leaves, the inside of the cell, the inside of that membrane, becomes increasingly negative, and the outside becomes increasingly positive. And now this establishes what we call an electrical gradient. We had a chemical gradient because of the difference in concentrations of potassium inside and outside. But now that potassium's leaving, we've created an electrical gradient as well across that membrane. And remember that opposite charges attract. So the positive potassium ions inside of the neuron are going to be attracted to the negative charge on the inside, which means that those positive potassium ions are going to become less likely to leave the negative interior. And at some point, the concentration and electrical gradients are going to balance each other out, and there is no longer going to be any net movement of potassium across that membrane. And this state of balance is called electrochemical equilibrium. And that electrical gradient that was created and that exists at electrochemical equilibrium is the resting membrane potential of the cell. Okay, so good so far. Now, I want you guys to think about what would happen if we opened up some more channels in the membrane. Okay, and by doing that, we're going to disrupt that electrochemical equilibrium. First, let's think about what would happen if we opened up some more potassium channels. Okay, these aren't leak channels. This is another type of potassium channel in the membrane that was closed before. So now we open it up. We've increased the membrane permeability for potassium. And as a result, more potassium is going to leave that cell. And when it does, just like before, it's going to take its positive charge along with it, which means that the membrane potential is going to become more negative. That membrane potential is going to be pushed towards a more negative value. And when that happens, we say that the membrane is hyperpolarized. Okay, so here I just put in a value of minus 85 millivolts. So if the resting membrane potential was negative 75, we've made the membrane potential more negative. And we'd say that our neuron is hyperpolarized. Okay, so the take-home message for that part is that if you open up potassium channels in a neuronal membrane, you're going to hyperpolarize the membrane. You're going to drive that membrane potential to an even more negative value relative to the resting membrane potential for that cell. Okay, so now remember, it's mostly about potassium when we're talking about the resting membrane potential, but there are a lot of different ions in the intracellular and extracellular solutions, not just potassium. And one of the most important ions for electrical signaling in neurons is sodium. And there's a lot more sodium outside the neuron in that extracellular solution than there is inside in the intracellular solution. Okay? Sodium, however, usually does not contribute a whole lot to the resting membrane potential, because even though there are a lot of sodium channels in the neuronal membrane, most of them are usually closed. They're shut. Okay, so there's no way for sodium to actually get through those channels and cross that membrane. It's kind of like even if there's a door, if that door is shut and locked, I can't leave or enter the room. Okay, so now let's think about what would happen if we suddenly opened up all those sodium channels. Well, sodium is going to come in. It's going to move down its concentration gradient. Okay, it's going to diffuse across that membrane, and it's going to enter the cell. Okay, and of course, sodium, like potassium, is a positively charged ion. So when the sodium goes in, it's going to be carrying that positive charge with it. Right, and that is going to make the membrane potential become more positive than the resting membrane potential value normally is. And in this case, we say that the neuron is depolarized. Okay? So, take-home message from that section is that if you open up sodium channels in the neuronal membrane, you're going to depolarize that membrane. You're going to drive up the membrane potential, and you're going to make it more positive relative to the resting membrane potential. Okay, so what can trigger these membrane potential changes, right? What actually causes ion channels to open or close, therefore making that membrane potential go up or down to create those electrical signals? Well, that really depends on the type of channels that there are. And there are all sorts of different ion channels that every cell expresses. That means that it has in its neuron. And I just want to talk about a couple different types, but this isn't a complete comprehensive list by any means. Okay, so for example, one big important one consists of the ligand-gated channels. Okay, so a ligand is a chemical that binds to a receptor or binds to a portion of another protein, and it causes a conformational change. It makes that protein change shape. Okay, so there are ligand-gated channels in the neuronal membrane, and when that particular ligand, when that particular chemical is present that can bind to that particular ion channel, it causes a conformational change. It causes the channel to open up, and once that channel is open, ions are free to diffuse in or out according to their gradients. Okay, another type that is very, very important in the generation of action potentials, and we'll talk about a little bit later, are the voltage-gated channels. Okay, and voltage-gated channels don't respond to a chemical signal. They don't open up when a chemical ligand binds to them. They open up in response to electrical signals along that membrane. Okay, so they actually respond to the membrane potential and changes in the membrane potential. In this case, there is a channel, and you see it over here. So this big sort of pink thing that looks like a hat is a membrane protein that forms an ion channel. Okay, and notice that parts of this protein are positively charged. Okay, since opposite charges attract one another, that means that this portion of the membrane channel protein is going to be attracted to the negative interior of this cell. So this would be extracellular and this would be intracellular side of that membrane. Okay, so this would be kind of, what you would normally expect, where you have something like negative 75 millivolts negative in here, and then you have a relative positive charge on the outside of the membrane. Okay, if an electrical signal occurs inside the cell, inside that membrane, then the inside of the membrane becomes positive relative to the outside. So this over here would be a membrane that has been depolarized to some extent already. Okay, and that depolarization, making the inside more positive, then causes that membrane protein to change shape, because the positive charge on the inside of the membrane is going to repel the positively charged portions of that protein. It's going to get pushed away, and that causes a conformational change in the entire membrane that opens up the pore in the channel and therefore allows ions to move through it. Okay, there are other types of ion channels that respond directly to physical stimulation from the environment, and we call these sensory transduction channels, and you can tell here the word sensory. So these are the types of ion channels that allow you to sense things, that allow your sensory neurons to respond directly to different types of stimuli. Okay, so for example, the picture here, this is a stretch sensitive ion channel. So this might be something like, if this is your, wow, this is a great picture. Okay, so if this is your hand, these are fingernails, by the way. There we go. Okay, anyway, so if you were to stretch the skin or do something to deform the skin and cause that skin to stretch, then the sensory neuron terminals that are innervating that skin would get stretched as well. And it literally can, that tension pulling on the channel can cause that stretch sensitive channel to open up, which would allow the ions to move through that open channel. Okay, so as you can see, there are lots of different things, lots of different types of signals that can ultimately cause ion channels to open or close. They could be chemical signals, electrical signals, or sometimes even physical stimuli coming from the environment. And all these different things have effects because they can trigger electrical responses in a neuron by causing ion channels to open and close, allowing ions to cross through that membrane, and therefore affecting membrane potential and triggering electrical responses within the neurons themselves. Okay, so the main points, first of all cells have membrane potentials. The membrane potentials of electrically excitable cells, like neurons, change when different types of ion channels in their membranes open or close. And that creates electrical signals that can be used to transmit or process information within the nervous system.